Morning. Today we're going to look at using Pascal's triangle to expand polynomials, binomials like this where we don't want to multiply it all out, and then developing a formula that we can remember that will allow us to figure out, instead of having to expand x plus y to the power of 10, now if we want the 7th term or the 8th term, we only have to find that term. So that is called binomial theorem. So here we have Pascal's triangle. The 5th row of Pascal's triangle, well, I've got 4 rows. This would be x plus y to 0, x plus y to 1, x plus y squared, x plus y cubed. Now, we can complete it to x plus y to the 4th. Now these are the coefficients, not the, doesn't include the variables, but these are the coefficients. But we can see a pattern here. If we look at x plus y cubed, it starts with 3 choose 0, and the k value increases until you eventually get to 3 choose 3. We're going to put the same pattern here for coefficients. We're going to start with 5 choose 0, 5 choose 1, 5 choose 2, 5 choose 3, 5 choose 4, etc. You're tired of me here to be talked about. Now, what do we know about the first term in any expansion? Well, it's going to be the first term of the expansion raised to the power of 5. So we're going to have x to the 5, y to the 0. Because when we have x squared, or x plus y squared, our thing is x squared plus 2xy plus y squared. Same thing with x plus y cubed. It would be x cubed plus 3x squared y plus 3xy squared plus y cubed. So what we're doing is that first term is starting with the highest power, the power of the expansion, and it's going to be decreasing all the way across. Okay, so that's our x. Now our y term, our second term in this expansion, is going to start at y to the 0, and it's going to increase all the way across. Now, because we are going to add these together, the only time we wouldn't add these together is if one of the terms was a negative value. Now this is the expansion. Now we haven't finished it because we have to figure out what 5 choose is. So this is going to be 1 x to the 5th plus 5 x to the 4th y to the 1 plus 10 x cubed y squared plus 10 x squared y cubed plus 5x y to the 4th plus 1 y to the 5th. Now again, I happen to have that rule of Pascal's triangle memorized, so that's the only reason why I was able to do that quickly. Okay? So here's our expansion. Now, notice again that we have, this is x plus y to the power of 5. There are 6 terms, because we started x to the 5th and end up with x to the 0, or started y to the 0 and end up with y to the 5th. There's always one more term, and one more term than the exponent of the expansion. It occurred in the 6th row of the expansion, or of Pascal's triangle, sorry. Okay, so again, x plus y to the 5th occurs in the 6th row of Pascal's triangle because we start with x plus y to the 0. Now, here's where we're going to develop our formula. The second term is from our expansion is 5 choose 1, x to the fourth, y to the 1. Fourth term is 5 choose 3, x squared, y cubed. And the sixth term is 5 choose 5, x to the 0, y to the fifth. Notice how the fourth term, second term, sixth term relates to the k value of the expansion, or a k value of the constant for that expansion. And notice again how it relates to the exponent of the second term within that expansion. The term is always one more than these two numbers that I have underlined in each expression. Again, notice here, this is 5 minus 1, this is 5 minus 3, this is 5 minus 5. So we could write this now. I would never do this, but this is how I get there. So again, we are relating the term to those ones I've underlined, and we're also relating the term to what we're taking away from 5 over the first term. Okay. Now this gives us, we just quickly looking at the pattern that we have here, why that says 6, looking at the pattern here, if we're looking for the tk plus 1, so if I'm looking for the 17th term, k would be 16. So if I wanted to know, as I do in the next question, the 7th term, k will be 6. Now, the term is always one more than what I'm going to use for k. So we have n choose k. We have the first term, which I'm going to write as x in this case. Because that's what's on the formula sheet, I would prefer the formula sheet to be writing an a, but it's what it is. And then it is raised to the power of the difference between n and k. And the second term, which I'm going to use y, is going to be raised to the power of k, where k is one less than term number. So n is the exponent of the expansion. K is one less than the term we're looking for. X is the first term. I've got the word term twice, and this is where it does get confusing. The first term, I am going to use that again. I know it's going to be a little annoying. And the second term. Okay. So when we have an expansion like x plus y to the power of the 11, and we're looking for the 7th term, really don't want to expand this fully like I did x plus y to the 5th. I'm only looking for one particular term in the expansion. So our n is 11, the expansion. K, since we're looking for the 7th term, k is 6. The first term is x in this case, and the second term is y. Now, in this case, it's also positive y. So using this here, which is on your formula sheet, we have 11 choose 6, x to the power of 11 minus 6, y to the power of 6. Again, when we get this here, at least with our expansion x to the 1, y to the 1, these two numbers, these two exponents will add up to 11 when we're done. So 11 choose 6. I have to go to my calculator for that. I'm assuming everybody else will also. Is 462. X to the 5, y to the 6. Much shorter than doing anything with the full expansion. Now, by the way, I basically cheated when I did it up here. I did do the binomial expansion because I knew this formula. Now again, why is k always one less than the term number? Well, our first term in any expansion is going to be 5 choose 0. That's the first term in the column. Everyone in the column here starts with 1 choose 0, 2 choose 0, 3 choose 0, 4 choose 0, etc. So it doesn't matter what we're starting with. The 27th term is going to be 26 choose 0. Hence, our k is one less than our term number that we're looking for. Now, this is no different. We want the fifth term. So I'm going to go through. N is equal to 8. That's what we're going to plug into our formula. K, we're looking for the fifth term. So K is 4. Now this is why, instead of using X and Y when I write this down, the first term is 2X, because X shows up too damn often here, so I'm going to change that a little bit. And the second term from our expansion is -1. So it's 2x minus 1 instead of x plus y. We have a little bit of different work to do, but not really. We have 8 choose 4. Now we're going to take our first term, which is 2x, raise it to the power of 8 minus 4. And I'm going to take my -1, and I'm going to raise it to the power of 4. Now, again, reach for your calculator to do 8 choose 4. 70. Now, what we have here is we're going to have 2x raised to the power of 4. Now, that is also raising 2 to the power of 4 in addition to x to the power of 4. Anything in a bracket has to be applied to both. And then -1 to the power of 4 is a positive 1, so we'll just write that. Now I'm just going to multiply 70 by 16. We have 1120 x to the 4 is our fifth term of that expansion. Again, I don't really want to expand something to the power of 8. I could. Not terribly difficult. It's a lot more work than is required. So when you're doing one with a different first term and second term instead of just x and y, you treat it in this manner. Now, for this guy here, what term of the expansion is of x plus y to the 7th is 945x to the 4th? Well, we don't really need to do much other than just find what the term is. So we have this x to the 4 is going to be useful to us. We know the binomial expansion, and again, I'm just plugging in brackets because I don't want to use x and y. The formula on the formula sheet uses x and y. What's useful to us is this, the n minus k. We know what n is, and we don't know what nck is. We don't know what this guy is going to be. We only really are looking at this one right here. Okay? We have our first term in here raised to the power of 4. So x is our first term, 7 minus k. We have to get x to the 4. So k has to be equal to 3. So k is equal to 3. Now I could do anything I wanted with the rest of it, but the question only says what term. Now we're not quite done because we always say k is 1 less than the term. So the term that this guy is, this is the 4th term. Okay, we really have to look at that and remember that that k value that we are using within our formula is always 1 less than the term that we're looking for. Again, going back to Pascal's triangle on the other page. And the reasoning again is everything starts off choose 0. Our first term within any expansion is going to be n choose 0. So the 17th term will be n choose 16 because of our starting point. The pattern that we developed through Pascal's triangle. Now, so again, the 4th term, and we don't need anything else for that. So in this case, we were looking at our first term, the x. There are problems out there where they're going to, it'll be nice, it'll be what term of x plus 2y to the 18th is some number x to the 7th, y to the 11th. Well, the nice thing about this is that's our k value right there. We don't have to worry about it if it's giving our second term, our second variable into that. Now, one term of the expansion is this really honking big number. What is the value of a if a is greater than or equal to 0? A can't be 0, but so all this is just saying is we're looking for the positive value. Now, again, we're going to have to figure out, we know that we know that n is 15. I don't know k. They didn't tell you what term to look for. We know that the first variable in the expansion is just x, and the second is a number, which we don't know, which is a. Now, if I could find k, I could probably do something here. Well, again, if we look at x to the 11th, we know that within that, x to the power of 15 minus k is equal to x to the 11th, because x is first within our binomial expansion. So just by looking at this, we can see k is equal to 4. Now, we are looking for the 5th term, but that's not really what the question worries about. Now, by finding that k, by a little bit of inspection there, now we can use the binomial expansion to figure out what a is. We have 15, choose 11, x to the power of 4, x to the power of 11, a to the power of 4. Right, so now that's equal to 21840 x to the 11th. I'm going to divide everything by 15, choose 11, x to the 11th. As we can see, the x to the 11th crosses off. So we have a to the 4, and now I'm just going to go grab my calculator, and I'm going to do that 21,840 divided by my 15, choose 11. This works out to be a to the 4 is equal to 16. I'm going to take the 4th root of that. So a is equal to plus 2 or minus 2. And going back to the question, they say a is greater than 0. So just ignore the minus 2 from there. So your value for a is 2. So this is a bit of a problem solving. Hopefully showing me that, or showing us that you understand the binomial expansion. Now, I could use Pascal's triangle for this, or I could use binomial expansion. So we are looking at n is equal to 4. Our first term is 2x, and our second term is positive 1. So n is equal to 4. Our first term is 2x. Our second term is positive 1. And our k value is 0, 1, 2, 3, and 4. We're going to use all 5 terms for that. So we're going to go 4, choose 0, 2x to 4, plus 4, choose 1, 2x power 3, 1 to the power of 1, plus 4, choose 2, 2x squared, 1 squared, plus 4, choose 3, 2x to the power of 1, and 1 cubed, and 4, choose 4, 2x to the 0, 1 to the 4th. So now we're not done. We have to tidy this up. We've got to make it look like an expansion. What we have is here is we have 1 times 16 x to the 4th. Because again, make sure that's 4. 2 gets raised to the power of 4. We have 4 times 8 x cubed plus 6 times 4 x squared times 1. I'm probably going to ignore that in that case. Plus 6. No, not plus 6. Plus 4 times 2 times 2x times 1 plus 1 times 2. Anything raised to the power of 0 is 1. So, and generally what we have is 16x to the 4th plus 32x cubed plus 24x squared plus 8x plus 1. Again, in an expansion, I did kind of cheat because I just also did use my patterns. But this is using Pascal's, or not Pascal's, the binomial expansion idea. Now the middle term, okay, very common question, middle term. Well, we have an expansion raised to the power of 11, or sorry, power of 10. What is the middle term? Well, there are 11 terms in this expansion. There's always one more term than the exponent of the expansion. So basically, I've got 11 terms, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. We have 1, 2, 3, 4, 5 terms on that side, 1, 2, 3, 4, 5 terms on that side. So now we now know by a little bit of thought process that we're looking for the 6th term. Okay, so the middle term of that expansion is what goes right between 1 and 11. So n is equal to 10, k is equal to 5. Okay, and that's the other thing. Your k value will be exactly half of your exponent. We have our first term is 3, and our second term is negative x. So we'll go ahead, plug it into our formula. We have 10, choose 5. That's always going to be the middle term of any row that has has a middle term. Some don't. 3 to the power of 10 minus 5, negative x to the power of 5. So no idea what 10 choose 5 is. We have 252. Now we have 3 raised to the power of 5, which is 243. And now we are going to have x to the fifth, but we have a negative 1 also raised to the power of 5. Since it's raised to an odd number, we're going to have our negative x to the fifth. And just quickly, 252 times 243, 61,236, negative x to the fifth. I would not want to do that in any other manner than using binomial expansion. So find your middle term. Anything that has an even exponent has a middle term. K will always be exactly half of that guy. I found it a different way here, but it is always half of that guy. There's your expansion. Now this one here is definitely a level of excellence question. I've never really figured out a way to do this without kind of a brute force method. So I understand where this might be a little confusing. So we are looking for the term independent of x, i.e. the x's in that term are going to cross off. Okay. Now we have x squared and we have 1 over x. Now, if I start brute forcing this from the right-hand side, I'm going to have x to the 18, x to the 17 divided by 1 over x. That's not going to cancel out things very quickly. So I'm going to start from the left-hand side, and I'm not going to write the exponents. I'm just going to worry about what's happening in the variables. Our 10th term is x squared to the 0, 1 over x to the 9. Doesn't work. Our next term is x squared to the 1, 1 over x to the 8. Doesn't work. We're not going to cross off. Next term is x squared, 1 over x to the 7th. Why am I thinking this might not work? X squared cubed, x squared cubed, 1 over x to the 6th. Okay, so this does work. I was wrong. What we're going to have with this term is going to have x to the 6th times 1 over x to the 6th. They're going to cross off. So I found that this is going to be my 10th, 9th, 8th, 7th term. And again, I don't really know of another way to do this other than what I call the brute force method. I did shortcut it because I knew I was going to have to start. It's going to be closer to the 10th term and it's going to be closer to the first term just because of the way we have an x squared to start with and a 1 over x down here. So now that we have the 7th term, now it's just a straight binomial expansion. We have n is equal to 9, k is equal to 6, 7th term, k is 1 less. Our first term within our expansion is x squared, and our second term is 1 over x. So now we just have to plug this in. We have 9 choose 6, x squared cubed, 9 minus 6, and x 1 over x to the power of 6. Well, we've already shown that those guys cross off, so our answer is whatever 9 choose 6 is. Okay, so the term independent of x, i.e. every other term is going to have an x in it. Therefore, every other term will have an x in it. This is the only one that the x's are going to cancel out. So I will see you in class tomorrow. Please bring questions if you have them, particularly understand on that last one.